that you could use this as a kind of type tagging. In fact, we don't do any type checking. We just assume that the argument that's supposed to be a table is a table. Okay? Why is that important? Well, let me walk over to this picture. So what's a two-dimensional table? Well, first of all, look only at the stuff above where my arm is. And it looks just like any table. It has a star table star, a sentinel node at the beginning, and then it has a spine, and each element of the list is a key value pair, except this is a key 1 pair, because we're going to have a key 1 and a key 2, right? We're doing a 2D table. So what we have is a plain old table of key 1s. Now, for the value, I've put ... here. Not as in goes on forever, but as in I don't want to talk about it right now. But there's one example that I actually worked out. So this pair in yellow, and this is something, it's a stupid little detail, but a lot of students get confused when they see this picture in the book, partly because the book is in black and white. So having this in yellow should really help, I think, if you're paying attention. This pair does double duty. As far as the first topmost table is concerned, this is just a key value pair, just like these ones, key value, key value. It's a key 1, the same as all those other key 1s. But now I'm showing you what its value is, namely not a table, but an association list. So the thing that confuses students is, why don't we need a star table star pair right here? And the answer is this yellow pair is the sentinel node for the table that includes it along with an association list. Okay? So it's not really a key value pair. The value is the pair, right? Because this pair is the sentinel node for the second table that has key 2 value, right? So the way you look things up in a two-dimensional table is you start by looking up the first key, treating this as a one-dimensional table, and you take the answer you get from a sock, not from get, from a sock, which is this key value pair, and you say, guess what? I'm going to treat this as my value, namely the table for the key 2s that go along with this particular key 1. Okay? Questions about that? Yeah. Yeah, we're making a two-dimensional table. So it's like the table that we used for data-directed programming, where there was a row key and a column key. So the row key is key 1 and the column key is key 2. Yeah? The question is, how do you differentiate between a one-dimensional table where the values happen to be lists and a two-dimensional table? And the answer is, you built the table. You know what you're trying to do with it. If it really bothers you, you could make that first pair say star 2D table star. If you want to be able, for some reason, to pass around both one-dimensional and two-dimensional tables mixed together. But ordinarily, that's not going to be the case. Ordinarily, the application that you're using means either that all your tables are one-dimensional or that all your tables are two-dimensional. However, one of the homework problems that you're going to do is to implement multi-dimensional tables where instead of having a key 1 argument and a key 2 argument and a key 3 argument, you have one argument that's a list of keys, kind of like a type signature, where you get all the keys together in a list. And use that to look up in a structure that can have any number of dimensions. And then the way you know is that you believe the user. If the user gives you a list of length 1, then you give the user back whatever the value is for the key 1, et cetera. Okay? All right, so again, this is not the world's most intellectually interesting point, but it's something that trips students up a lot, how that pair serves double duty. If you look at it from above, it's a key value pair. If you look at it from below, it's the sentinel node of this second table. By the way, how long does it take to look something up in this table? Theta of what? What's n? The number of elements in the table. Nope. Somebody raise a hand. Don't just mutter, because I can't hear the muttering. Yeah. The number of keys. Yes. It's the number of key 1s plus the number of key 2s in the worst case. Half of that in the average case. Because in the worst case, what we're looking for key 1 turns out to be the very last key 1. And then when we get to the second layer table, it's the very last key 2. So it's the total number of key 1s plus the total number of key 2s. So it's linear in the sum of two things. But that's less than if you implemented this table. There's a simpler way to do two-dimensional tables, which is just to make the key be a list of 2 words, right? And check both keys at once in a single linear table. And the problem with that is that then it would be, the running time would be the number of key 1s times the number of key 2s. Because that's how many key 1, key 2 possibilities there are. So this is a little bit more efficient in time at the cost of a little bit more complicated data structure. Okay? Right. Should we use equal or EQ when we're looking to see whether the keys match? Okay, let's take a vote. Who votes for equal? Who votes for EQ? Okay. You're both right. It depends on what you're doing. In all the situations in which we've used tables, and we'll use tables in this course, the keys are symbols. Since they're symbols, they are EQ if they're equal. So it does, oh, wait a minute, I take it back. There'll be a couple of situations coming up down the road in which we use numbers as keys. And remember I showed you last time, 2 numbers that are equal are not necessarily EQ if the numbers are very large, like more than plus or minus 2 billion. And so if you have numeric keys, then it's the right thing to use equal to make the comparisons. If the keys are just words, it doesn't matter. If the keys are lists, then it depends whether you mean to test that these 2 lists look the same or whether you mean to test that it's the identical list. So you would use either EQ or equal in that situation. Because it depends, we have actually 2 procedures for looking things up in association lists. The other one is called ASSQ. ASSQ. Sounds kind of funny, but that's its name. Which is just like a SOC, except that a SOC uses equal to make its comparisons, and ASSQ uses EQ to make its comparisons. Okay? So you get your choice.